what I want to do here is I want to explain this diagram, this temperature enthalpy, specific enthalpy diagram, and in doing so, helping to give you an understanding of where the equations that we use for wet vapor come from, and how the vapor changes from its liquid phase through its evaporation phase into its dry vapor and superheated vapor phase. And this is what this diagram here represents. When a process, whether it's in the boiler or whether it's in the condensing process, when it changes phase, either in terms of evaporation from liquid to vapor or condensation from vapor back to liquid again, it goes through this period of evaporation. Now it's also a constant pressure process. So this diagram is showing what happens to a vapor, in this case H2O, in terms of its properties, its saturation temperature, its pressure, and so on, as it changes phase from its liquid phase to its vapor phase. Now there's a series of lines here, and basically if we follow this line here, so up to that point, and then horizontally, whoops, across to here, and then out into there. Sorry, the mouse is very hard to control. This line here is all it's at constant pressure, and it represents the change of phase of a liquid which is at 26 kilonewtons per meter squared as it changes through from liquid out into superheated vapor. So beginning down at this point here, where we have our liquid, and we start to add energy to it. So as we add energy to it, and adding enthalpy to it, as it shows in the horizontal axis, then the temperature increases. And it's going to increase until it reaches this point here on the saturated liquid line. At this point, the vapor starts to boil. It's reached saturation point. And at a pressure of 26 kilonewtons per meter squared, or 26 kilopascals, it will saturate or boil at a temperature of 66 roughly degrees Celsius. So that's the point at which the vapor is going to start to change from its liquid phase into its vapor phase. Now you'll notice that as the evaporation process continues along this line here, there is no change in temperature. So what's happening here is heat is being added, energy in the form of heat is being added to the vapor in latent form. It's called latent heat, meaning that it's latent means hidden. There is no rise in temperature as the substance changes from its liquid phase into its vapor phase. Basically what's happening is all of the energy added during this period is used up in breaking the bonds and changing its phase from its liquid phase into its vapor phase. Only when you reach this point over here on the saturated vapor line, the dry saturated vapor line, do we then see an increase in temperature again as we come out into the superheat region. So all of these lines you're seeing here, if you keep going back to this point down here and you follow the line along the saturated liquid line, the next point we're going to make our way across is this one, and then continue. If you were to do the same process along to this one, and so on and so on, these are all at constant pressure. So the next line is 0.34 mega newtons per meter squared, or 0.34 megapascals. So at that point, when the H2O is at that pressure, it saturates at roughly 138 degrees Celsius. That's the point it begins to change phase. And then eventually it's going to come over to our dry vapor line. And it's continued to do that. And this loop we're seeing here, this loop is it's joined up all of the saturated liquid points and all of the dry saturated vapor points. And we have this loop. Anything inside that loop is wet vapor. Now, depending on where we are in relation to either the saturated liquid line or the dry saturated vapor line, will depend on how dry the vapor is. When we're on the liquid line, it's completely wet. It's all liquid. When we're on the dry vapor line, all the liquid is gone. So your dryness fraction ranges from 0 on the liquid line all the way up to 1 on the saturated vapor line. And in between, you've got these three lines here that are all showing dryness fraction from 0.25, 0.5, 0.75, and then 1 over here. And it would be 0 on this one over here. So it always, regardless of what pressure the H2O is at, it has to go through this period of evaporation. Now there is this point up here called a critical point, and that is the point where it stops behaving like a vapor and begins to behave as a gas, which is something different. A vapor and a gas behave slightly differently. So we're looking at a vapor. So, and anything to the left of the liquid line, if you remember from refrigeration and heat pumps, is under cool liquid. Anything to the right of the dry saturated vapor line is superheated vapor. The definition of superheated vapor is a vapor that has gone above its saturation temperature at a particular pressure. For example, if we take the 0.34 megapascals line, when we come out into the superheat region, the temperature starts to increase. So choosing any point on there, we've now gone above saturation, and by that amount there. And the distance between the two is what's called the degree of superheat. That is, how far above saturation temperature have we gone at that particular pressure. So whenever we're dealing with vapor that is wet, that is anything under that loop, there are equations that we apply in order to calculate the amount of energy it's taken to get it to that particular point. And before I discuss these equations, if we just look at this diagram here, so that's just simply taken one of the samples off that diagram at a particular pressure, and it's showing all of the enthalpies that relate to the different parts of the process as it changes phase from liquid into superheated vapor. So this line here, this point here is our boiling point. That's this point up here. This point here at 0.4 relates to the point where it reaches dry vapor. 0.5 is superheated vapor. Anything between 0.2 and 0.3 is our period of evaporation. So in terms of the enthalpies, enthalpy is H. Now there's all of these notations, F, G, Fg, and then just with no notation H. These expressions relate to the vapor steam tables. Sorry, the tables that the wee book that I advised you to buy. And in that booklet, it gives us properties of H2O as it's increased in pressure and temperature and as it changes phase at particular pressure saturation temperatures. And what you'll be going to doing is, when it comes to calculating energy quantities, energy transfers in the boiler, for example, or in the turbine, or if it was in the feed pump, then we'll use the tables to extract enthalpy values from it. We'll also be using charts, and I'll explain the charts in a separate commentary, that make it easier for us to get enthalpy values throughout a vapor power cycle. So in terms of these notations then, HF refers to the enthalpy of saturated liquid. That is the amount of energy to take the sample of H2O up to boiling point at this point here. So it's the enthalpy of liquid. So the phase of the H2O at this point is liquid. The enthalpy of the vapor when it reaches dry saturation point is Hg. So Hg refers to the amount of energy to get our sample of H2O up to dry vapor. The bit in between the two saturation lines is the period of evaporation. And the enthalpy that takes us from one saturation line to the other is called the enthalpy of vaporization, and it's given the notation HFG. And I shall see HFG is equivalent to Hg minus Hf. Once we continue past 0.4, we're into the superheat region. We've now gone above our saturation temperature, TS. And the enthalpy, as it's listed in your tables at this point, is just H. So there's a reminder then of what all these terms mean. HF is the specific enthalpy. Specific means per kilogram. All of your quantities in the steam property tables are listed per kilogram. Specific enthalpy of saturated liquid is HF. HFG is the specific enthalpy of evaporation, or vaporization as it's called sometimes, and that is the period between the two saturation lines, liquid and dry vapor. Hg is the specific enthalpy of the dry vapor, and H is the enthalpy, specific enthalpy of superheated vapor. Now, you'll notice that in order for us to evaluate the enthalpy up to dry vapor point, that is 0.4 here, then it's going to be HF plus HFG to get us from point 0, if you like, up to 0.4. That is to get it up to dry vapor. It's going to be HF plus HFG. If I was to go back a little bit, and let's say I was to go back to, say, this point here, I haven't quite reached 0.4. So I'll just make that line a bit thinner. So we haven't quite reached 0.4. So what that means is, if we wanted to evaluate the enthalpy to get us just to this point here, where this line is, then it's going to be HF plus a portion of HFG, not the whole of it, but a portion of it. And the term that's used at this point here is X, and that represents dryness fraction. So as I said, over at 0.2, dryness fraction is 0. At 0.4, it's 1, in which case it would be HF plus all of HFG. But if I had only reached, say, 3/4 of the way along this period of evaporation, then that means that X would be equal to 0.75. So I've gone 3/4 of the way across, so it'll be 0.75. That means that to evaluate accurately the amount of energy to get us to this point here, it's going to be HF plus 0.75 HFG, or X HFG. So it's HF plus X HFG to evaluate the enthalpy to take us to any particular point within the evaporation stage if we haven't reached all the way to 0.4 and dry vapor. We can also apply the same equation for entropy. In one of the examples in the study pack, before we start looking at the chart, we will use the steam tables to evaluate, and also the entropy equations to evaluate the dryness fraction. When we come to using the chart, it makes life so much easier, as you'll see. But when we apply enthalpy or entropy to any period within 2 to 4, then these are the two equations we have to apply, where again HF is the enthalpy or entropy of liquid, HFG or SFG is the enthalpy or entropy of evaporation or vaporization. And you'll also, as I said, HFG or SFG is simply Hg minus HF, or in the case of entropy, Sg minus SF. So hopefully that gives you a little bit of an insight into where these equations are used and how we evaluate the energy quantities, particularly in this area of evaporation. This chart is our enthalpy entropy chart. When we solve problems in steam and vapor power cycles, and when it comes to evaluating enthalpy values, we can either use the steam tables, the vapor property tables, or we can use this chart. Now, the use of this chart makes life a lot easier. And this chart is used in particular to show the expansion through the turbine. And what you can do is, you can assume initially, at least, regardless of the question ultimately specifies this or not, you can show isentropic expansion through the turbine as a vertical line on this chart, because if you remember, isentropic expansion means constant entropy, which would be a vertical line on the chart. When we plot the actual expansion through the turbine on here, we can quite easily extract entropy values from the chart rather than having to do it from the tables. So if we look at the makeup of the chart, vertical axis shows enthalpy up both sides. Along the horizontal axis, we have entropy. Now, looking at all of these lines, the lines that go from the bottom left-hand corner of the chart and slope up until eventually they become horizontal lines over here are temperature lines. And you'll see the temperatures here going from 100, 200, all the way up to 800 degrees Celsius. So these lines there are lines of constant temperature. The lines that make their way again from the bottom left-hand side of the chart and sweep up to the top right-hand side of the chart are lines of pressure. And it's pressure in kilonewtons per meter squared or kilopascals. Quite often, we're dealing in bar. The conversion, if you remember, from kilonewtons per meter squared to bar or kilopascals to bar is divided by 100. So, and vice versa, if it's bar to kilopascals, it'll be times 100. So, for example, if we have a pressure of, in a question of, say, 10 bar, then in order to express that pressure in kilonewtons per meter squared, as it appears in the chart, we would times it by 100, in which case it would be this line here of 1000 kilopascals or 1000 kilonewtons per meter squared. So we have lines then of temperature and lines of pressure. Now, if we look at this, there's a sort of separating line. You can see this line where the chart seems to sort of change in nature all the way along to here. This line here is the line, our dry saturated vapor line, if you like. Anything under that line there, this line that begins here and comes down over to here, this line that sweeps up like that. Anything under that line is wet vapor. And you'll see that the dryness fraction lines are given. So we've got 0.75, 0.8, 0.85, 0.9, 0.95, and then eventually up to 1 here. So anything under there is wet vapor. Very often, as the vapor expands through a single turbine, it would normally go from superheated vapor down into wet vapor. So we would be starting up in this region here somewhere and probably coming down and finishing our expansion somewhere in our wet region. So we're going, what's the next device after the turbine is the condenser. And a typical condenser pressure can be something in the order of 0.04 bar, or in the case of this chart, 4 kilonewtons per meter squared, or maybe 5 kilonewtons per meter squared. So if I was to show a line, a typical expansion line in a turbine on this chart, then let's say we have a temperature of, let's say, 500 degrees Celsius, and we have a pressure of, let's say, 20 bar, which is going to be equivalent to 2000 kilonewtons per meter squared. So where the 2 points intersect, our 500 degrees and our 20 bar or 2000 kilonewtons per meter squared is going to be at this point here. Now, if we assume isentropic expansion, then we're going to get a vertical line until and let's say our condenser pressure is 0.05 bar or 5 on this chart, 5 kilonewtons per meter squared. Then if I draw a vertical line from our intersection point and stop when I get to my pressure of 5 kilonewtons per meter squared, then that is my expansion through the turbine, isentropic expansion through the turbine. And if I label these, then this would be, if I call that point 2, then this point here would be point 3, and it would be point 3 dash. Now the dash represents ideal expansion. Whenever you see that dash attached to an enthalpy or other properties, it's referring to ideal values, isentropic expansion. So it's a case now of simply projecting across to our horizontal axis to read off the enthalpy values. So if I do that in both cases, and I project horizontally across, then I have my enthalpy values. Now, that's a far easier process, particularly for 3 dash, than it would be using the steam tables and our equations for wet vapor. Now, quite often, the expansion through the turbine is in the equations is not isentropic. And again, we can use this chart. Having derived the values for H2 and H3 dash, we can apply our equation for the isentropic efficiency of the turbine in order to evaluate the actual enthalpy at exit from the turbine. And that equation comes from here, where on this diagram, TS diagram, it's showing the Carnot cycle, but it's showing the compression and expansion on the dotted lines as the actual lines, as opposed to ideal lines vertically. So depending on whether we're looking at the compressor or whether we're looking at the turbine, then these are the equations that relate to our isentropic efficiency. So if we look at the turbine one, then if you think about power outputs, the ideal power output of the turbine is going to be higher than the actual power output of the turbine, because in the actual process there's going to be losses and therefore less of a power output. And the biggest value is always going to go on the bottom of the equation. So the efficiency of the turbine is the actual output divided by the ideal output. And the outputs, if we express them in terms of changes of enthalpy, then it's going to be H2 minus H3 over H2 minus H3 dash, where H3 dash is our ideal enthalpy at exit from the turbine. So if you use that equation, knowing the actual isentropic efficiency of the turbine, we can transpose it for H3, and that then gives us the actual enthalpy that we'll use to evaluate the energy transfer in the turbine itself. So with a combination of the chart and of the equation for isentropic efficiencies, then we can derive the enthalpy values, which we'll then use to put into our equations for the energy transfers in the devices, either turbine, boiler, or feed pump, or as compressor as it's listed here. The actual enthalpy drop through the turbine using an isentropic efficiency is going to be less than it would be for ideal. So what you'll find is that H3 will be at a value higher than H3 dash. So for example, if we were to choose, let's say we've applied an equation for isentropic efficiency and we've found that H3 is, say, let's say 2500. So if I project a line across at 2500, in order for us to show the actual expansion now through the turbine, then I would simply join up point 2 and the intersect between our pressure, condenser pressure, which in this case is our 5 kilonewtons per meter squared. Then it's a case of following that line until it intersects our 2500 enthalpy line, and then join up to the start. So this diagonal line here, which is H2 to H3 now, the actual enthalpy at exit from the turbine. That is the actual expansion, as opposed to the ideal expansion being 2 to 3 dash. So this chart then, it's used to show the expansion through the turbine and allows us easily to extract enthalpy values without having to apply the equation so often and the steam tables.